Hi, my name is Rachel Thomas, and I'll be speaking about the paper Highly Accurate Protein Structure Prediction with AlphaFold. This paper was published in Nature in July 2021, and it addressed the problem of how to take an input sequence of amino acids, given as a linear sequence, and predict what the 3D structure of the protein would look like, even when structures for similar proteins were not known. This paper was the result of the winning entry in the 14th Critical Assessment of Techniques for Protein Structure Prediction, CASP 14. This is a competition held every other year to predict recently solved protein structures. So there's something called the Protein Data Bank, which is a large database of 3D protein structures. And as new proteins are discovered, some are not added to the data bank right away, but rather are held back for this competition. As a little bit of background, kind of prior to machine learning, or if you're not using machine learning, people often use a rules-based approach for solving problems. And this involves handcrafting relevant rules for a problem. So for protein structure, that would be having a score about hydrogen bonds that kind of explicitly teaches an algorithm that hydrogen bonds exist and that they should be formed. For a game like checkers, that would be explaining the rules of checkers. And this image is a picture of Arthur Samuel, an IBM researcher who came up with the term and the concept of machine learning in the 1950s. And he taught a computer to play checkers without ever telling it the rules. So he didn't tell it, you move diagonal and you jump over pieces. Instead, what he did is he read a lot of previous checker games into the computer. Similarly, what AlphaFold and other machine learning approaches do with protein structure prediction is that they give the computer program a large number of previous PDB protein structures, but they don't give it any explicit rules about things like hydrogen bonds. So figure 1A in the paper shows just the top 15 teams and their scores in the competition. And you can see AlphaFold is number 1. And here, lower scores are better. The measure being used on the y-axis is a measure of how close the predicted structure was to the actual structure. So this is a distance. A shorter distance means that the prediction was more accurate. And you can see that AlphaFold is significantly better than even the second place team. In total, there were 146 teams in the competition, but this just shows the top 15. And the measure being used here is alpha carbon root mean square deviation. And so that's looking specifically at the distances between the alpha carbons. Figures 1, B, C, and D just give 3 examples of particular proteins that were in this data set, showing in blue what AlphaFold predicted the protein structure to be, and green was the true structure that had been determined experimentally. You can kind of see that the proteins range in complexity. And the protein pictured in 1D is a 2,180 residue protein with no structural homologs. And AlphaFold still did well on it, although not as well as the simpler proteins. Also, a point out for later that you can see even the second through 15th place teams, in general, their median alpha carbon root mean square deviation was closer to 3 angstroms, whereas AlphaFold was around 1 angstrom. And I'll kind of reference that later. So figure 1E shows the model architecture. And so machine learning models involve a lot of matrix math. You're starting on the left with the input sequence, so a sequence of amino acids. And this is represented in 2 key ways. And I'm actually going to zoom in on this part of the diagram because I think it's really important, and then I'll come back to the whole thing. But one is that the input sequence is represented as a multiple sequence alignment representation. And so this is seeing what other sequences of amino acids that have been discovered are similar. And this can be across many different species. It captures evolutionary info. If you've ever used programs like BLAST, this is capturing some of that, of looking what are the other sequences that are similar. And then the second way that the sequence is represented is for a pair representation. And so here the matrix kind of along both sides has the sequence, and it's trying to come up with an estimate of how far each amino acid would be from each other amino acid. And this captures a lot of physical information about physical properties of the amino acids and how they might relate to each other. So going back to kind of this whole model architecture, you have these two different representations that are fed into the model. Then there are 48 evoformer blocks, and there'll be a diagram later going into what mathematical operations are in an evoformer block, but it's just a series of math operations. Those are then later fed into 8 structure module blocks, and there'll be yet another diagram showing the math operations in those. This whole thing is, well, I should say what comes out on the other side is then a 3D structure of the protein. However, these operations are all repeated 3 additional times, so 4 times in total. And they call that recycling. In this paper, a lot of places would call it machine learning epochs. Figure 2 is all about validating that AlphaFold works for other new proteins in PDB. So they didn't just test it on the ones in the CASP14 competition, but even after the competition ended, they continued working on this paper and tested it on other proteins. For figure 2a, they specifically chose proteins that had been newly discovered and were not very similar to existing proteins, and they created a histogram of what the alpha carbon root mean square deviation measures were, and you can see here that most of them fell in the 0.5 to 1, which is an excellent score, or 1 to 2 range, which again is very good. And if you'll remember back from the initial figure I showed you of teams 2 through 15, they had a median of 3. So here AlphaFold has continued to perform quite well in predicting the structures of these new proteins. Figure 2b is looking at a local measure of the alpha carbon residue, and basically showing when the backbone is accurate, the side chain accuracy is high. And so I'm actually going to, I'll come back to this slide. First, I want to talk a little bit about metrics, since there are a lot of different metrics on these slides. And I found that a bit confusing. And so for me, it was kind of helpful to break it down. But the metrics used in this paper are kind of split between global metrics, where you're getting one number for the whole structure, the whole prediction. So that includes the alpha carbon root mean square deviation that I've already discussed. There's also something called the TM score, which is the similarity between the actual and predicted, and this is less sensitive to outliers than alpha carbon RMSD. And then for the purpose of this paper, they came up with a new measure called PTM score, because you need to know the actual ground truth to calculate the TM score, and while the algorithm is computing, it doesn't know that, and so they kind of came up with an approximation. And then there are also some local metrics that are used, and that lets you kind of make a prediction about different parts of the protein of how accurate those are. So going back to these figures, 2b is showing that when the backbone is accurate, the side chain accuracy is high. And so on the x-axis, they're using this local measure basically on the backbone, and then saying what fraction of rotations were predicted correctly. Figure 2c compares a local confidence metric to a local accuracy metric. And so this is important for your model its confidence is how the model can't actually think, but how likely its answer is to be correct. And so it's good for the model to know what it doesn't know and when it's not confident about a prediction. And then figure 2D compared this new metric I mentioned that they had created, PTM, which is useful because you can calculate it as you're still doing your calculations without knowing the ground truth, and found that that was a reasonable approximation to the TM score, which you need the ground truth to calculate. Figure 3 dives into this evoformer block that I mentioned before. There are 48 of these in the model. It's a series of math operations performed on the multiple sequence alignment representation as well as the pairwise representation. And it's just a series of math operations. You can see with the arrows kind of how things are flowing through it. And something to note is many of these are triangle operations. And so basically, with the amino acids, they're not just looking pairwise at how do two amino acids relate, but since this is a 3D structure, it's really helpful to look at how would three different amino acids all relate to each other. And so they have a number of triangle computations, which are shown in B and C, where they can, so here they've chosen three amino acids that they're calling I, J, and K, and showing how those all relate to each other. And doing computations on that. And they don't do all combinations of three in the model. They just kind of pick various ones, but to capture more of the 3D structure or 3D interactions. Then they also, if you'll remember back to the overview, there were 8 structure blocks. That's a different set of mathematical computations closer to the end. And the output of this is, so they're kind of predicting various rotations and translations. And the outcome is to predict the angles of the different atom positions. And so you can see in figure 3D kind of how the information is flowing through the math operations. And then 3E is a visualization of kind of you're getting this very mathematical series of angles coming out of what the protein structure is like, and then you can kind of transform that into kind of what the atoms and the molecules would look like. And they call this a residue gas in the paper, but it's a representation of each residue as a free-floating body. And then figure 3F shows what they call the frame-aligned point air. And here green is the predicted structure and gray is the true structure. So I particularly liked figure 4. So in machine learning, you often will have a lot of different kind of new innovations you've added, or a lot of different types of computations you're doing. And it's important to see, are all of those actually necessary? And you can do something called an ablation study, where, so here, if they've added 10 new things, try taking them out one by one and see how the model performs. Do you actually need all of them, or are some of them redundant or unnecessary? And they showed that you do need all these techniques that they're using because they're all contributing. And so here they've shown that, and so you can see kind of how the score gets progressively better with the different techniques added, is what figure 4A is showing. In figure 4B, they're looking at kind of, do you need all 4 epochs, or what they called recycling, where they're going through these math computations again to update their values. And with some proteins, so this just graphs 3 particular proteins in blue, orange, and green. Blue and orange were simpler proteins, and AlphaFold got it right after one iteration through. And remember, there are 48 blocks, so getting to 48 is kind of one epoch. But some of the more complex ones, it really did need all 4 to get a better score, and that's what's going on with the protein graphed in green here. So they did need the whole time for this. Then figure 5, this is, I think, a really interesting point, and this is part of the discussion. But they found that accuracy was much lower when there are less than 30 sequences in the multiple sequence alignment. So being able to find other sequences, even if they're not closely related, but that have some relationship, is really, really crucial. And otherwise, it does hurt the accuracy. However, once they got past, and so notice that the x-axis in figure 5A is on a log scale. Once they crossed about, I believe they said 100 sequences, accuracy really didn't improve that much. So there's not really a benefit to, if you have 100 sequences in your multiple sequence alignment, you don't really need more than that. And figure 5B showed that AlphaFold got very high accuracy predictions for homomers, even when the chains were very intertwined. And so a homomer is a protein that's kind of interacting with itself a lot. Yeah, so moving into the discussion, AlphaFold learned from existing protein structures in PDB with very few explicit rules. I thought it was really neat that in this paper, that even when it was published, it was already being applied. It has applications in X-ray crystallography, in cryogenic electron microscopy maps. I already mentioned the finding about how many aligned sequences you need. Something that was pretty neat about this is that at the same time it was published, a companion paper was also published in Nature, applying this to the entire human proteome. And previously, that's a problem that would have been impossible because it was too slow and expensive. AlphaFold did struggle with proteins that interact with a bunch of other molecules. So if they have few interchain or homotypic contacts, and I think it makes sense that those would be harder to predict. But overall, AlphaFold really kind of blew away all the pre-existing techniques for doing this with its high accuracy, and has been a big breakthrough in predicting protein structures. Thank you.